Very good. So now we have Sebastian Mizera from the IAS Princeton telling us about the towards the geometric color kinematics duality.
Thank you, Ricardo. First of all, let me say that it's an absolute pleasure to be here, and I thank for the organizers for the invitation. So today I wanted to tell you about some things that I've recently learned about color kinematics duality, which have completely changed my point of view on this topic. And I promise you that by the end of the talk, you will have a slightly new perspective as well. So let me start by very quickly reminding you what color kinematics duality is. So let me consider scattering amplitude in a massless gauge theory. So here the notation is that L denotes the number of loops and N is the number of external legs. Let me organize the loop integrand as a sum over trivariant Feynman diagrams gamma, and this can be always done in this trivial way by rewriting contact terms in terms of trivariant ones. Then later on, we have the obvious symmetry factors as well as product of propagators for all internal edges. And in the numerators, we have color numerators, C gamma, which are typically contractions of structure constants of your gauge group, as well as the rest, which we call kinematic numerators, N gamma, which are polynomials in polarization vectors, momenta, etc. Now let me consider triples of diagrams, gamma S, T, and U, which could be part of some bigger diagram and that differ only by these 4-point interactions. And they're organized in precisely such a way that they differ by these two structure constants, such that they satisfy the Lie algebra Jacobi identity. The sum of these color factors is always 0 for every possible triple of diagrams gamma S, T, and U. Now you can ask, what about the kinematic numerators? And of course, the ones that naturally come from Feynman rules do not satisfy these kind of identities. However, they're also not unique. So for example, we can shift them using generalized gauge transformations. And this allows you to hope that perhaps we can impose the so-called kinematic Jacobi identity, which looks like exactly like what we've seen before, but now with C's replaced with N's for every possible triple of diagrams gamma S, T, and U. And let me just emphasize that this is a very difficult problem because it involves a huge number of constraints for a huge number of variables. However, if you manage to do this, there's a large reward because you essentially get a gravity scattering amplitude for free by simply replacing these color numerators with another copy of kinematic ones. We obtain the gravity integrand. So that's a famous result of Bern, Carrasco, and Johansson. So over the last 12 years, there's been a huge amount of progress, up to 4 loops, and including a range of different quantum field theories. So we've heard about those topics in every single Amplitudes conference and as well as in talks this week. So this structure hints that perhaps there's something universal about color kinematics duality, which is purely fixed by the combinatorics. So the question you might ask is whether there exists a geometric version of color kinematics duality which is fixed purely by combinatorics of relations between various Feynman diagrams. And that's an idea which is very similar to what Carrasco told us a few years ago. So let's consider a partially ordered set of Feynman diagrams for a fixed number of loops and legs, for example, L equals 2. And at every step, we do this usual thing that we add a propagator in all possible ways. And after exactly 3L plus N minus 3 steps, we land on trivariant diagrams. And now the question we want to ask whether the existence of these triangles here, or like the pure the way that they fit into the structure, has something to say about color kinematics duality. And my main motivation for trying to approach this geometrizing strategy is a belief that if there exists an abstraction for a high enough number of loops, then that abstraction would have to be topological. And we want to formulate our problem in such a language that a possible abstraction would be easier to see. So what I'm going to do is consider the following object, I'm going to talk about it more globally than what you might be used to. First of all, let me consider the space of all possible kinematic numerators n's and n tildes. Inside of this, what I want to identify is a subspace of those numerators that satisfy Jacobi identities for every possible triple gamma S, T, and U. And these are the blue and green regions here, and they're mutually orthogonal. Second of all, what I want to do is consider another subspace, and that's a subspace in which this combination remains constant. And of course, that constant is what we want. The physical interpretation is as tree-level amplitude or a loop-level integrand. And in this language, the question about color-kinematics duality becomes whether the intersection of these regions is non-empty or not for a specific constant. And the way I organized it here, the problem naturally splits into two pieces. One are these linear constraints, and the second problem are the quadratic constraints. So this defines what we need to do. And what I'm going to say in this talk is, first of all, I will approach the linear constraints, these ones. And in particular, this will give us a geometric meaning of kinematic Jacobi identity. And I promise you, this is going to be extremely simple. And it's one of those things that once you see it, you won't be able to unsee it. Second of all, we will move to quadratic constraints. And that turns out to be much more difficult to do in practice. So we're going to approach it at tree level or L equals 0 first. And my approach will be the one naturally given by intersection theory. There's also an alternative approach described in this beautiful paper of Frost and Mason, who used Penrose transform to similar end. So I invite you to look at this paper. If there's remaining time, I will also describe how to extend this approach to loop level. And even if I don't have the time, there will be a related talk by Casali in the afternoon on a similar topic. Okay. So where do we even start? Well, first of all, we need an organizing principle for trivalent diagrams. And as you might remember from your graduate classes, Riemann surfaces are precisely those objects that in various different limits give you various Feynman diagrams. So what we want to consider is a configuration space or moduli space of Riemann surfaces with exactly L handles and N punctures, denoted with this symbol. Let me remind you how this looks like in the simplest case, which is MO4. In this case, we are talking about configurations of spheres with 4 points each. Three of those points we can fix by conformal invariance, and that leaves us with 1 degree of freedom, for example, Z2 here, which parameterizes our moduli space. So some point here might correspond to a specific configuration such as this one. And what we want to look at is now configurations in the neighborhood of these dangerous points. So what happens when Z2 approaches Z1, one way of thinking about it as putting a lasso around these 2 points and then shrinking it to 0. In this way, the surface bubbles into 2 Riemann spheres connected by a point. You can repeat the same story when Z2 approaches Z3 and when Z2 approaches Z4. And these things already look like SD and U channel diagrams, and we call them boundaries of the moduli space. Of course, this generalizes to arbitrary L and M. One type of boundaries that we have is the one that we've seen before. And now we also have a new type in which you can put a lasso around the handle and then shrink it to 0, and it gives you this kind of degenerations. Now, at every step, the dimension of the corresponding moduli space decreases by 1. So after exactly 3L plus N minus 3 steps, which is the dimension of the moduli space, we land on something which is purely fixed. And that is going to be given by configurations of spheres with 3 punctures each. And I will exclude tadpoles for the purposes of this talk. And as you can see from this example, all of the spheres are in one-to-one map with trivalent diagrams, such as this one. So if we call the corresponding diagram gamma, then the place in the boundary of the moduli space where this happens, I will denote by V of gamma. So now we would like to approach this problem a little bit more algebraically. So what we're going to do is put a differential form. It's going to be a degree 3l plus n minus 3 holomorphic form on the moduli space MLN. So the analog of taking boundaries is now doing residues on this differential form. And in the simplest case, this would be residue when two punctures are being equal. And at each step, the degree of the form decreases by 1. So after exactly the same number of steps as before, we land on a zero form or a scalar denoted with this symbol. So by this symbol, I will mean a residue around the corresponding vertex is a composite residue in a chain corresponding to a given degeneration corresponding to a graph gamma. Now, this leads us to a natural proposal. What we're going to do is just pick a single differential form, phi, and then by doing residues in various different ways, which are already in one-to-one map with diagrams, I'm going to assign numerators as the value of this residue. And strictly speaking, here we're talking about equivalence classes of differential forms. And that's because if we deform it by some exact term like this, well, the residue of d of something is always 0, so it doesn't matter which representative of this equivalence class you take, you always get the same numerators. And here's a few remarks. Well, first of all, this limit in which the surface becomes fully degenerated is also known as the tropical limit, which gives you some way of describing coordinates close to these degenerations. Second of all, let me emphasize that the residue here is not a unitarity cut, and in particular, kinematics is fully left generic. And finally, I'm going to require that my differential form as a function of kinematics is local, and that means that it cannot have any kinematic poles, denominators. So here's a claim. Numerators assigned in the way that I just showed always satisfy kinematic Jacobi identity. And here's a sketch of a proof. So let me consider one step before the final degeneration. So what this corresponds to is that there will be exactly one sphere somewhere in the middle and with exactly 4 punctures, and everyone else will be fixed. So let me denote the punctures which are fixed by z, s, t, and u, and the one remaining degree of freedom as z. So our moduli space now became one-dimensional, and we have a dizzy form, which is obtained by a chain of residues, except for the last one. Okay, so the remaining moduli space now is exactly what we've seen a couple of slides before. And what we want to do to extract numerators is simply doing this final residue. Okay, in this case, it corresponds to residue of z around zs, and that will give us some BCJ numerator for this particular graph. Likewise for t and u channels. And now we can do the obvious thing, just deform this contour to a point, and that gives us, by a residue theorem, then these numerators assigned in this way always have to adapt to 0, and you can repeat this argument for every possible triple of diagrams gamma s, t, and u. So that proves that numerators assigned in this way are always BCJ. So let me summarize what we've done so far. We managed to trivialize the constraint of kinematic Jacobi identities by coming up with the spaces of differential forms, which map injectively to a space of BCJ numerators by taking residues appropriate to a particular numerator. And now this informs a way that we could approach the quadratic constraint. Well, what we want to do is take 2 differential forms, and we want to come up with some way of pairing them up that would give us this kind of objects. So from now on, I will specialize to tree level, or L equals to 0. And let me notice first that so far there's been no physics input. We just had these spaces of differential forms, which are mathematical objects. But what we need to do is now to connect the fact that singularities on the Riemann surface are supposed to correspond to kinematic space singularities. And this can be done by coupling my differential form to a gauge potential. So I'm going to choose it in such a way that for this potential to remain finite, any possible singularities when punctures collide would have to be compensated in the numerators by zeros in the kinematic channels, like so. So in this way, what I can do is just slightly deform what I had before. And now, instead of considering spaces of forms with this usual derivative, I can couple this derivative into a covariant derivative with this gauge potential. And I will do it with a minus sign and with a plus sign here. This forced us, because notice that the potential itself has non-trivial mass dimension, and this forced us to introduce some mass scale, which I will just call mu, for this to be dimensionless. And I will come back to the interpretation of mu in a second. So in order to avoid confusion, I'm just going to call this space of differential forms as ordinary forms, and the ones that we're interested in as twisted forms. So one interesting thing is that these types of differential forms are well known to geometers, and that allows us to study some questions that we might be interested in physics, translate them to geometric questions, which in this case turn out to have known answers from a long time ago. And moreover, those answers precisely match with what we expect from physics, what we know and love, these two numbers. So that means we must be on the right track. So this might be all dry. So let me just give you some concrete example. So what we're going to do is consider 4 points, and let me use this gauge fixing for simplicity. One example of a twisted form is this one, which is poles at 0 and 1. And in the numerators, it features some spinors and polarization vectors. So you might already see where this is going. Another example of a differential form would be something similar, which has pole at 1 and infinity, and then in numerators, it has color matrices. Now, what we'd like to come up with is some way of pairing up these two forms to get numbers, okay? So the simplest way we can do it is simply to pair them up by integration. So we're going to wedge together these two forms and then integrate over the moduli space in an appropriate sense. This will give us some numbers, and we call those intersection numbers of these two twisted forms. And what we've been exploring for the past couple of years is that the fact that these forms give us some tree-level amplitudes in various theories. So let's see how this works for these examples. If you actually compute it, it gives you this answer. And you might compare it with a Feynman diagram computation for this QCD process involving quarks and gluons, and it precisely agrees. And now we know the interpretation of this mass scale mu in our example. It's simply the quark mass. However, the thing that I wanted to emphasize on this slide is that the way that the answer comes out here, well, it's a correct QCD amplitude, but it sort of comes in this one package. And it doesn't obviously split as a sum over trivalent diagrams. So what we would like is some way of manifesting the fact that it gives us trivalent diagrams. And here's just to flash you that this is not just one example. By now we know that amplitudes of various theories have this kind of representations, including massive and massless particles. But from now on, I will specialize to massless external states only because I wanted to make connection to color-kinematics duality in the simplest setting. So let me summarize what we have so far. We came up with these spaces of differential forms, which are coupled to these gauge potentials such that they know about kinematic singularities. And by simply integrating them by this intersection product, they map to tree-level amplitudes. And now the thing that we want to explore is whether this space has some overlap with the two previous ones. And strictly speaking, we already know that this is the case. So the real question is, how does it happen geometrically? And one thing that you might already expect from very naively, what we want to do is suppress these kind of terms And that means that we want to take this mass scale to infinity, or in other words, we want to take the low energy limit of this case. As a matter of fact, what we're going to do is consider two separate kinematic limits. So an example spectrum coming out of these kind of computations involves some massless and massive states, which might be what we've seen before. And one limit is the low energy limit, in which we take this mass scale and all the massive particles decouple. And that's what we're going to need for Color-Kinematics duality. You can also consider exactly the opposite limit, the high energy limit. And in this limit, all particles will become massless. So there's two reasons why I wanted to discuss this first. First one is to make connections with previous talks. And the second one is that for massless theories, so if there's no massive particle to begin with, or the intersection number is independent of mu, then these two limits just coincide. And this will give us two different ways of thinking about the same object. So let's consider the high energy limit first. What you can show is that it's the formula that you obtain is this one. So we have a residue localized on these kind of constraints with these pairings, all the subleading corrections are known in terms of these so-called higher residue pairings. And one thing that I wanted to emphasize on this slide is that this story is completely general, and we can apply it to various different spaces and not just for MON. That's a thing that we've been exploring for a couple of years now, and I wanted to flash you some examples that are of physical relevance. Well, first of all, as you might recognize, these derivatives of potential being equal to 0 are nothing but scattering equations. And as a matter of fact, that's the formula that we've learned from Cachazo and Yuan. And in this interpretation, W was, as before, the potential on a Riemann surface. And we learned in the talks yesterday by Cachazo, Guevara, and He that there's also interesting generalizations to other types of projective spaces. Another place where these kind of formulae appear are in topological CFTs or in Seiberg-Witten theories, in which now instead of the mass scale mu, we have an H bar, and W is a superpotential for a given theory. And lastly, we have a case which is very interesting for multi-loop Feynman integrals. In this case, instead of mu, we consider 1 over epsilon, where epsilon is the Dirichlet parameter. And the potential W now is a potential on a Feynman graph instead of a Riemann surface, at least in one interpretation. And we'll hear more talks on related talks by Brito, Karan Watt, and Dur today and tomorrow. So finally, let me focus on what we are actually interested in, which is the low energy limit, or the one in which we have the tropical degeneration. In this limit, what you can show is that we obtain this formula as a sum over trivalent diagrams with propagators and with numerators given exactly by what we wanted. And by previous arguments, these are already guaranteed to satisfy kinematic Jacobi identities by default. And that gives us the BCJ representation. So here's just a few remarks. First of all, you need to be a bit more careful when these twisted forms have some explicit mu dependence, because there's some non-commutation of limits issues. Second of all, for massless theories specifically, or alternatively, when these twisted forms are logarithmic, the formula is exact, meaning that there's no corrections at all, because there's no mass scale. And finally, there's many possible generalizations that I invite you to think about, especially those two massive external states, perhaps working out these explicit formulas for the subleading corrections, which might involve something like contact diagrams and so on. So here is just a final example. If you wanted to compute an amplitude for massless pions, you can do it by intersecting these two forms, and they're given as follows. It will give you this answer. However, if you wanted to just obtain numerators straight away, what you can do is pass it through the residue machinery, and it gives you the color numerators and kinematic ones for free. So since I'm out of time, let me just finish briefly by summarizing what we've done. We've defined a new strategy for approaching the color kinematics duality by splitting it into linear and quadratic problems, and then asking to geometrize it in terms of Riemann surfaces. Then we define some spaces of differential forms on moduli spaces of those Riemann surfaces, such that the kinematic numerators can be obtained by performing residues on those forms. Then we ask ourselves how to pair up these differential forms such that they give us invariant objects. And the answer was provided by these twisted forms whose intersection number corresponds to a scattering amplitude. And finally, we ask ourselves about the overlap, and that overlap was given to us precisely by the low energy limit in which we made the connection with these regions. So with that, let me thank you.
Okay, well, thank you very much, Sebastian. Well, the first question will be by Yara, who cannot raise his hand because he's a co-host. Yara, go ahead.
Yeah, hi, thank you very much for an interesting talk. So I know that you mostly here spoke about the tree-level case.
Yes.
I just want to ask, because your aspiration was to resolve some of these higher loop problems as well. There is, as you very well know, there is a problem with labeling the loop momenta.
Yes.
For the non-planar case. So I wonder if this is kind of an input there, and so you have to resolve it before, or if this suggests some resolution.
It's a wonderful question, and as a matter of fact, it does propose a resolution. So let me briefly talk about it. So first of all, we wanted to be very precise about the space of numerators, so we need to resolve some of the ambiguities. And one of them is whether to consider total derivatives or just make this just an actual constant, and that's what we're going to do. Second of all, we have this loop labeling problem, which is what you're asking about, and that's happens just to, the question you want to ask is whether to identify these two graphs that just differ by assignment of loop momentum, or just make some unique choice. So what we want to do is pick some unique choice. Now let me tell you how this is, the solution to this is provided by Riemann surfaces. So in the standard picture of chiral splitting, what we do is we assign the loop momentum by measuring it alongside these red cycles, L1 and L2. And then what happens is that when punctures go around and they pierce these cycles, the loop momentum is now measured, in this case, around here and around here. So that would be the giving rise to the labeling problem. However, what we want to do is to define the loop momenta uniquely. And what that amounts to on a Riemann surface is precisely by slicing the Riemann surface. Okay, so what we end up with is this kind of surface, which is called a border Riemann surface, such that punctures can no longer pass through. Okay, so this gives us some definition of how to define uniquely loop momentum, except for one additional redundancy is that now we have to decide in which way exactly do we want to slice our surface. And one choice is provided by this choice of picking one point and then do all slices through that point. And that's exactly what we've been interested in pursuing. So in those cases, what you can see is that, or what we expect is that by previous arguments, away from the slicing, everything just holds as it used to, because the arguments that we made before were local. So now what we want to consider is what is the effect of this slicing on color kinematics duality. And that turns out to be a very interesting story that we've been pursuing with Casali and Turkin, and it gives us some interesting connections to string theory, monodromy relations, tropicalizations, and Bernoulli-Casari rules. So you will hear more about it in the talk by Casali.
So just a quick follow-up. So the prescription is the same as Piotr Turkin proposed in one of the previous papers. So that's that prescription that you will use.
You cut the. Sorry, there's two pieces. One is how you choose these A cycles, And the additional idea is that you actually want to slice the surface, so don't allow punctures to pass through.
Okay, thank you.
That gets rid of the ambiguities.
Okay, before we continue with the questions, let me just say something in case people start tailing off to their short break. Well, I want to thank all the speakers this morning. We will restart at 1:15 as planned. And let me just say that if you missed out on the conference photo yesterday, you can take a picture of your little rectangle and send it to Anastasia, who has kindly agreed to put them together. Now, let me give one more question that comes out of the co-host, so it doesn't show up there, by Zvi. Go ahead.
Yeah, hi. Yeah, it was very, very nice. Just a follow up on Yara's question. You mentioned some understanding of obstructions, let's say at 5 loops and beyond. Do you want to just elaborate for just a minute on that?
Right. There's a very speculative let me just escape here. So there's a very, what you're asking about is basically, what we've shown is that you can define these spaces of differential forms. Sorry, I'm looking for, the slide here. We've defined these, how to obtain BCJ numerators using these differential forms, but I didn't say anything about how to exactly choose these differential forms. So the way it has been working at tree level so far and giving rise to these families of differential forms are these specific choices. And I'm not going to get into exactly how their specific structure, but roughly the guiding principle to where they come from is to start with a superstring correlator, which is defined in RNS formalism on a supermoduli space, and then projecting out the fermionic directions on this moduli space. And that's a step that we have to do, is go from the supermoduli space to the moduli space. At tree level, this is given simply by integrating out these fermionic directions. Okay, it's very simple. And then you might ask, does this guiding principle for obtaining specific twisted forms extend to higher genus? And if you take an assumption that that's your guiding principle, then that would necessarily have to break down at least at 5 loops. Because of there's precisely a geometric obstruction, which tells you that you cannot go from supermoduli space to you cannot project it down to a bosonic one. But I have to say that's a very wild speculation.
Good. Thank you.
Thank you.
Okay, next we move to Henry.
Okay, can you hear me?
Yeah.
Yeah, okay. Hi, Sebastian. Thanks for a nice talk, by the way. Yeah, so I guess I had the same question as Yara and Zvi, but I guess I can ask a slightly different question. So you said you wanted the intersection between the Jacobi rendered for the n numerators and the n tilde numerators.
Yes.
But then I'm wondering, we know that when, for example, when we do double copies, we can often relax one of the.
Yeah.
So does that change your analysis anyway, or?
It will change it at some point. I wanted to do just the simplest case. What you're referring is that basically what we're asking if this region is non-empty or this region is non-empty.
That's right, yeah.
That's a weaker statement. And I didn't explore this direction, but I agree that that's a path forward.
I guess I can also add a comment maybe to this 5-loop problem, because that's an interesting problem, which I thought about it a bit, and so this will be some speculation, but I mean, imagine if there's no problem at any loop order when you write down BCA numerators for n equals 4 CPI mills, then you would expect that would have to have some explanation, that there would be perhaps a supersymmetric Lagrangian that manifests BCA, at tree level Lagrangian. But we sort of know that that cannot be the case, because you cannot have a supersymmetric Lagrangian which makes n equals 4 supersymmetry manifest off shell, right? So it's quite possible that, you know, if we encounter some problem, it's not actually due to Jacobi relations, but rather due to the supersymmetry. I mean, the fact that we impose local supersymmetric numerators together with Jacobis, which is sort of, you know, telling you that we have some underlying cubic Lagrangian there, right? So the problem could be more due to supersymmetry. So I'm wondering, if you relax supersymmetry, do you see that's, I mean, do you have some intuition whether relaxing supersymmetry would help?
No, I don't have much intuition. Yeah. I have to say that one of this motivating beliefs was that the abstraction would have to be in some sense topological. And what I meant by this is simply that we have some way of this assigning local data, the triples of numerators, and they overlap because triples of numerators can share diagrams. So there can be some global abstractions. And that by itself doesn't say anything about, you know, specific matter content of your theory. So other than the speculations that I mentioned to Zvi, I don't have anything in addition to that.
Right.
But thank you. That's a great question.
Okay, Chashan.
Yeah. Thanks for a beautiful talk, Sebastian. I wonder if you can comment more about the mass in double copy.
Yep.
Because one trivial way at tree level at least is just do dimensional reduction to get mass into double copy.
Yeah.
But it seems like in your formulation, mass arises more naturally. So do you see, for example, including mass would give abstraction, or you can see a solution when you include mass into double copy? The recent papers, they study, say, double copy of massive graphitons, but then they see some abstraction, say, beyond at 5 point, I think. And maybe I don't know if we can say more about that.
I'm not sure I can say anything concrete, but let me just mention that the intersection numbers by themselves, they seem to work very well with massive particles, and that's like exemplified maybe by these theories, which, you know, this one considered by Johansson and collaborators contains massive particles, and we can describe it to arbitrary multiplicity. One of the things that I wanted to focus on is this case of massless external states, specifically for the double copy, and that's where we get this beautiful formula here. And I haven't explored much the cases, that's what I was mentioning here, extending this to massive external states, and that would be needed for these cases from the recent papers on massive Galileans and gravity.
Would there be a crucial difference adding mass into internal states, or?
So let me just, so to summarize, what I'm saying is that for intersection numbers themselves, I don't think it's a problem. The other questions, if there's some nice limit which we can take, such as an analogy with this one.
Okay, thank you.
Okay, I'm afraid the next question will be we will last now because we have to check the slides of the next speakers. So Atul, go ahead.
So I was just going to ask, that was a super clever talk, but I was just going to ask a slightly speculative question. I was wondering if you had this Riemann surface which was labeled by, which had punctures labeled by Mandelstam invariant ZS, ZT, ZU. I was wondering if it had any connection with the kinematic spacetime that Nima was talking about, who also had this two-dimensional strip labeled by Mandelstam invariance, because it does seem that what you're doing is fairly twistorial, also in the sense that it seems you're just taking the twistor space of the full kinematic space itself.
Are we talking about tree level or loop level?
I don't remember, but you just had this identity, right? N gamma S plus N gamma T plus N gamma U equals 0 coming from the residue theorem.
Yeah.
Yeah, it was just a speculative question. Do you think it might have some relation with the kinematic spacetime that Nima talked about?
So let me just say that there's this beautiful story that Nima and Song have been exploring, which is which they call the stringy canonical forms, which are special cases of the twisted ones. So that fits very nicely at tree level, and they can, with this formalism, and you can map it. They know very well how to map it to the kinematic space. But I don't have many comments on how this would extend to loop level.
All right. Yeah. Okay.
Okay. So maybe now we maybe make a break to start moving to the next session.